Okay, today we have an MITP seminar by Kushal Chakraborty. He joined as a postdoc in December. He's going to tell us about fermions in higher state.
Yeah. So, for the background of my talk is fermion and high spin. So, again, we all know what fermion is, and no, that's different, but let's understand what is high spin is. Yeah. So in literature, we don't know that we express particles in terms of their mass and their speed. So if any particles is spin greater than 2, we call them high spin. And so in string theory, these particles are natural. In string theory, we have why is particle important? Because in string theory, we already have all these particles with high spin, and their speed depends on their and the mass depends on the string length. But the thing is that in standard model, I mean, this type of particle, they do not operate standard model. So in standard model, the highest speed particle is basically spin 1, we don't have any particle spin 2 and more. So the thing is that how you can realize this, the question is how you can realize these high spin particles in normal quantum field theory. And another important thing is that, I mean, some of you may know that, I mean, if we have a theory of gravity, and if you want to include the algebraic interaction that means terms which are basically some quantity and basically are basically or then and to prove that, I mean, the theory is causal, I mean, there is no time in constant, we need this we will have to have this interaction of high spin classified. And this was argued in this paper by Malvina. So that's why I mean this high spin particle is important. And we'll use the scattering as a method to study this high spin particle. So what is the scattering? What is time advancement? Okay, so it's basically, let's say, we know that I mean nothing can go faster than light. No signal can go faster than light. But the thing is that I mean if we just include this let's say this high energy connection, so we see that everything I mean there will be process which will go faster than light. And then this is the random. Why do you want to realize this particles in theory? I mean, so basically, let's say someone says that okay, I mean, speaking theory is just okay. We want to realize something in the language of the quantum field. You know that string theory, this thing automatically come, but there could be one way where you can understand it in the philosophy model kind of thing. Or isn't it that Weinberg-Witten theorem that says that nothing like this can happen? Nothing like this can highest in particles start appearing in these local field. The massless particles can't appear in theory. I mean, the maximum field is spin 2, but there is no system in MITP. And these particles are all MITP. Okay, I mean the statement is the massless high spin particle can the masses can appear, but they will not interact. Yeah. So I mean we see scattering in our everyday life. I mean, for example, there is the scattering of this billiard ball, and even in this room the scattering of this air molecule. I mean scattering is everywhere. And so we know that one of the famous experiments by Rutherford we take the atomic structure where I mean you use the alpha particles and he just convert these alpha particles on a gold foil and then he basically say that what is that atomic structure. This is the famous scattering experiment. So we know that studying scattering from a very long time. And in quantum field theory, I mean, we realize this type of scattering in terms of Feynman diagram. So this is a Feynman diagram where you can see that this one electron at positron, they just annihilate with a photon, and then again, I mean, they just create these photons can play in the electron. So this is a example of wave production. This is represented by this Feynman diagram, and also there is this counter scattering where a photon can scatter with any charged particle, and then I mean then we get a charged particle and a photon with a different difference. So this type of interaction, I mean, there is the thing is that there could be a Lagrangian which will govern this type of interaction. And one famous example of this Lagrangian of this QT, where you can see that this type of interaction for gas production is basically governed by this type of fiber gamma side. I think it is the proton field, and this side which is basically the Fermion field. So the goal is, I mean, if you want to realize this type of interaction of the high speed particles, first we have to construct what is the suitable term in the what is the term that we have to include in the Lagrangian. I mean, or basically what is the interaction term. So, what is the criteria for a term to be a valid to represent a valid interaction? This type of interaction they should satisfy certain symmetry. I mean, they should be invariant under certain symmetry. I mean, let's say here we have a field and we just transform this field by some operator. And the thing is that, I mean, the interaction term, for example, in this case, this type of term, phi bar from A inside, and this type of term would be invariant under those symmetry transforms. So this symmetry transformation can be some continuous symmetry transformation like the quantity transformation, or the Gaussian transformation in non-relativistic theory, or they can be, you can also demand some discrete transformation like charge conjugation, parity, time inversion. These are the discrete transformations. And so for a theory, for a relativistic theory, we want our this interaction to be quantity. So quantity group is the symmetry group of relativistic theory, and this type of interaction that I was talking about. For example, this type of term, this term is basically invariant under the quantity transformation. So this thing will just map to itself. So this is the quantity invariance is the basic criteria for any theory, any interaction term of any interaction term. I mean that should be invariant under the quantity transformation. So now the question is, I mean, let's say we construct such an interaction term. The question is, I mean, are these terms that we have constructed are become unique? The thing is that, I mean, we can just redefine the field, and if we can, so then, I mean, if I can get one term by defining a field from another interaction term, just we consider those two terms to be same. They can be invariant under they can be related by field definition, or they can be related to each other by some property. So these two terms, which are basically related by some field redefinition or total objects, they basically describe the same process. So that's why, and all by the same process, I mean they will represent the same scattering process. That's why we first want to construct the scattering, because we first want to look at the scattering process, and then we will use that model to construct the Lagrangian. And you know the if someone comes with a different type of programming, you expect the same, I mean basically the same. Two things are same. So in this talk, basically I will be talking about the triple function of two massless particles, with one is massive high-speed particle. So here is a schematic diagram of two massless particles, diagram of two massless particles and a massive particle. That is small phi, you can think of that massless particle, this capital Y massive particle. This massless particles can be photon, can be scalar, can be graviton, and even can be spinor, the fermion. Now, why one mass? Why this one? Why not some higher? So in any scattering process, we have mainly two types of one is the constant, where you can think of all the particles basically interact at some point, or we have some exchange diagram. For example, this is the exchange diagram. So one example of contact interaction is you may consider, I mean, hyper theory. The hyper which is a contact. Maybe. So let's say Lagrangian of this point. So this term, 5/4, looks like this. So this type of term, which are basically formed from some field, and at some point, this type of term are called conductor. And then we can have some interaction term for some exchange diagram. So this type of diagram, one can see that these particles I1, phi P1 and phi P2, different momentum. They are coupled to a massive hydrogen particles, and then again they create this two-bit pi drive. So here the interaction is done by a massive by a thing of this pi. Process. So that's why I'm 3-point function are considered as a basic building block to market the hydrogen category.
I'm maybe naive about these things, but when you draw this three this scattering matrix to this process, so then you impose energy and momentum conservation.
Yeah.
But you need more for off shell, off shell to go to get the full thing for the bottom one, right?
No, so you will put the external particles on shape, so they will satisfy equation of motion. And then the outer thing is basically you are considering the loop diagram.
Okay, yeah, that's true. This thing that doesn't have
yeah, these are all together.
Yeah.
So basically you have the particles phi.
Yeah, that one doesn't have loops, yeah, sure. So yeah,
Yeah. So you will also particle loop. So one thing is basically, so this type of process, so they also have a basic for your whatever you may include your loop and whatever. And these will also have very basic. So okay, I will come to that. But definitely expect this. So you consider any particle.
Yeah.
What I'm talking with some external particles, there is some momentum, there is some polarization. And the thing is that any scattering amplitude you can break as a let's say a function which will be depend on the momentum, and a function which will depend on polarization and momentum. And there will be some. So these terms, these are called tensor vectors because they are basically made up with the polarization. They form a basic. So if you found that for some process, if that thing is vanished, so there is no way that you include loop and whatever. Whatever I will you consider in your theory, you will not get this that. So they are basically formed as a basic. So you can also consider them as a basic. So this is basically say 4 particles basic. Yeah, so this 3-point function, they also have a basic for.
Sorry, I'm lost. So in 3-point functions, 3 particles are interacting at one vertex, right? And there are also 4 particles are interacting at one vertex. So I don't understand how. I'm confused of how that is contact from this system.
Okay, this is the exchange diagram. So next I want to try some interaction with the output. So I can have some diagram, let's say something. This is a contact interaction. Or also I can have some term. This type of diagram already comes with it. So this type of diagram are called exchange diagram. This is term. And contact interaction is basically where all the field, yeah, they will not interact at a point. There will be no such particle exchange. So that's the any details, then you do not have any other question. So let's now, so let's understand what is the notion of particles in quantum field. So in quantum field theory, we usually describe particles by their mass and their speed. There will be some other traditional degrees of freedom, but mainly and basically there are some number and a particle is described by that type of number. We call this mass and speed there. So any particles, and also we represent these particles as a irreducible and unitary representation of the in terms of the symmetry, which is in this case is the quantum. So I will explain what is the irreducible representation. What is the irreducible representation? And so the thing is the quantum group, which is a non-compact. And we know that any non-compact group, they have the unitary and irreducible representation in finite dimension. It's very hard to work with them with this infinite dimensional representation. That's why we tend to represent particles in terms of their state. So the little group is a group which is inside of this quantum. So this may form a subgroup of the quantum. And we represent the particles in terms of the irreducible representation of this little group will be compact, so their time will be finite. The irreducible representation of finite dimension. So let's first understand what is a irreducible representation. So consider a vectors in a three-dimensional space, and you can just apply a rotation group, or you can just rotate. You may just rotate the vector or the coordinate, and I can just transform them to a different set of vectors. And here, this is the rotation group. Here the rotation group acts on the leaves the z-axis invariant, and it transforms vector with different. So either you can just represent them in this metric form, or you can just in the more compact notation, which is basically between time, which is basically this r times v. R is basically the component of this rotation. So R is. So now, what we say is this vector, they form a representation. The representation is the representation of the rotation. Because the rotation group has the action of this vector. And it can just convert one vector to another. Now we can construct a more generalization of vector, which is a tensor. So consider a tensor of rank 2, which is basically V of I being constructed from. You may think of V of constructed from the product of two vectors, which is V of I, V and U. So and this is how this tensor transform under this group. For each indices in this field, we have one R, and or we can just represent them in the like the previous case in this case like a matrix. So this here is basically this tensor P, and A is basically some matrix which is an angle. Now, if we know that if two matrices are related to each other by some similarity transformation, they basically belong to the same class. So we can do a similarity transformation, and what we can do is that this matrix I can break it into a block diagram. So I can break this 9 cross 9 matrix by a 5-dimensional block, 3-dimensional block, and 1. And if we just have it, so instead of this T of I J, I can construct from this T of I J some other set of tensors, which is basically A, which is a symmetric tensor, defined symmetric tensor, defined this way. A is a antisymmetric tensor, which is defined this way, and 5 is a and so in this basis, what I can do is that so this A is basically the 9 plus 9 matrix. There is a 5 plus 5 block. That is 3 plus 3 block, and there is 1. And then we have this and so from this we can see that if you just apply this matrix name on this vector, this basis, then the A will transform them on themselves, A is transformed on themselves, phi transform on themselves. So if there is there is such a structure where I can further reduce the my operation of the matrix, I mean, so each of these S, N, S, A, and phi, these are irreducible representation. We cannot further reduce this block. So these are irreducible representation. So given an action of some operator on some vector, some tensor, if we can just reduce them in a block diagonal form, then we call that reducible representation. And if we can't further reduce them, we call that reducible. So that's the meaning of reducible representation. And one can think that, I mean, basically the reducible representation is just transform among themselves. So they form a vector, invariant vector, and that's why it is reducible representation. I mean, the question so far.
Well, we make some assumption that you can break up the points into vectors.
Did you find it as a tensor product? Did you find the IJSB could be IJ?
So you're defining the tensors.
Yeah, it's not any tensor by product.
It's linear combination of products.
Yes.
So the tensor has more components than two vectors.
So yeah, so
Tensor has more components than.
So DIJ in 3 dimensions will have 9 components, and these have 9 components.
It's a product.
It's
just constructing tensor representations of SU3 and the Benny's SO3 and these reducing to the irreducible representations. Additional magnitude effect.
Yeah.
1 plus 1 is 0, 1, 2.
Yeah. You can always construct a tensor by product vector, and then you impose the symmetry. So each of these things that is the symmetric tensor A will be the symmetric tensor and will be here. They form a reducible representation of the group, which is the rotation group in 3 dimensions. And now basically is sometimes that I have talked about this little group. I mean, we represent the particles as a reducible representation of the little group. So in this space-time dimension, the reducible representation of the little group is for the massive particle is SOD minus 1, and the massless particle is SOD minus 2, which is the special orthogonal group of the rotation group in D minus 1. So any particles will be like the representation of some of these SOD. So the question is how we can represent, how you can denote this reducible representation of this SOD. So let's consider this the group of SO2n or SO2n plus 1, and we can represent this the reducible representation. They are represented by a set of numbers, which is the any set of numbers for SO2n plus 1, and then uniquely describe your reducible representation. So for example, I mean in SO3, which is the rotation group, and from the environment, we know that if we know N, I mean basically represent particles as in 3 plus 1 dimension as spin 0, spin half, spin 1, spin 3 by 2. These are basically the orbital, or even these are the L, the number L. And then from each you have M, which is minus 2 plus. So if we know L, we know what is the particle. So here in high dimension, we need a set of L, which is the any number basically L. And from there you can see that for SO3, basically n equals to 1 and you have only 1. And this number you can think of as a element of your rotation generator. This so basically let's say in for SO2 and SO2 plus 1, I have this rotation generator with J1 to J3 for J2 and J1, and we just represent the particles as a quantum number of this one. So I think we can work with this notation, but this notation is complicated. So that's why we choose a different notation to denote a reducible representation of this histo group, which is basically the young. Okay, so far there are many questions. So what is a young tableau? The young tableau is basically you can think of as a certain collection of blocks, and they are arranged in certain manner. So in this case, I mean, we have a row of G, and this represents a tensor of asymmetric symmetric tensor of rank. Similarly, I can have a column of length J, and they represent a antisymmetric tensor of J. So all these different blocks, different collection of blocks, they basically form a reducible representation of the histo group. So you can think, I mean, each different size of different shape of box corresponds to one reducible different reducible representation. And then we can have, I mean, it's not that only symmetric and antisymmetric tensor. I can have some tensor which more structure. Like I can have some tensor which have some antisymmetric indices and symmetric indices. T, which have 3 antisymmetric, and then which is antisymmetric in mu2 and then symmetric in mu4. So these are all represented by this type of structure, and they are all reducible representation. This type of structure is called a symmetric tensor. And there is one-to-one correspondence between each representation and each vector.
Was that notation supposed to suggest that it's symmetric in mu1, mu2, mu3, mu4?
No, it's not symmetric in mu1. So you can have choose two different state of physics. One is symmetric and another is antisymmetric. So if you let's say if you want to choose the symmetric in mu1, mu2, mu4, then with antisymmetric because mu1 is one and top. So it is the choice of physics. So let's just work in this antisymmetric. So whenever we see a column, it's basically whatever the indicator in that column is, it will be antisymmetric in that column. And if there is some row, I mean this is there, that will. So as here I mentioned that any physical representation of the equation of 20+1 is basically can be denoted by a set of n numbers, and this n could be true for the young. So any young tableau is uniquely described by a set of numbers, basically from let's say L1 to Ln, and these are basically the length of the row. So the first row has box L1 number of box again, so L2 number of boxes. And there is a restriction on the number of rows, which is basically the n. You cannot have any young tableau or any tensor which is more than n number of rows. And this basically says that I mean you cannot have any independent tensor of this SO2 and resistance plus 1 with more than n number of n. So now as we know that I mean how to represent the reducible representation in terms of young tableau, then we can just construct the 3-point function. Because as I mentioned, any interaction term with 3-point function is also interaction term should be a pointless scalar. So I have to construct a scalar out of the field of the massive particles and the massless one. Or in principle, I have to construct a scalar out of this young molecule. And a photon, which is a massless particle, in three space-time dimension, a photon is basically represented by by a vector representation of this, so v minus 2. So a vectors which is 2 not by young term in this, and this epsilon is the polarization. The polarization is really nothing but we can discover the Fourier transform of the vector of the field. And any massive, I mean, there is no restriction for the spin of this massive particle. Massive particles can be represented by a general irreducible representation of by. So this is phi is the massive particle, and this is the polarization of this same.
Sorry, how about a massive vector?
A massive vector, I mean, basically you have only mu1, and all the
You distinguish that between photon. Massless, I mean, photon is a massless vector.
yeah.
And then how do you represent a massive?
Which basically you represent them as let's say some finding, but it will transform under a to b minus 1, not a to b minus 2 in this space time. So any massless or massive particular given here, they are irreducible representation of the SO group, or spin, I can say more precisely the spin group, the double cover of SO group, but they are basically
Why for photon d minus 2 does it have something to do with the polarization?
yes, that's what it is. I will come to that why. Yeah, because photon has two gauge. So if you just subtract the two gauge, then you will get it d minus 2. Okay. And y went from massive particle y, so d minus 1 is different outcome. So this is how we represent the particle is basically virtual representation or a lambda. So we want to construct the 3-point function of let's say 2 photon and 1 arbitrary spin particles. So again we have to basically we have to construct a scalar out of this the field or the whatever the independent quantity we have, basically the polarization of the photon and the polarization of the massive particle and their moment. That is the thing that we have, and we have to construct a scalar out of it. And as we are dealing with photon, then this structure subject to the gauge invariant function. I mean, if you can demand some other symmetry like the parity and universal or the charge configuration, that's up to you. I mean, you will just impose each of the symmetry, and you will construct you will see one of the invariant and the bound symmetry, and those will be the value of the sequence or any other. So the massive particles, which is let's say phi, which is a massive particle. Here I'm not talking about. Here I'm not mentioning what is the symmetry. And they satisfy this transformation. Apart from the equation function, they also satisfy this branch. But this mu can be any index. I mean, this derivative can be constructed to any index of the massive scale phi, massive field phi. And so what is suggested in momentum is that the polarization is basically orthogonal to the moment of the massive particle. So hence polarization has one degree of freedom. And in this space-time dimension, if you include that one dimension, the range is basically a to minus 1. So that explains why it transforms under a to t minus 1. So let's say you construct a space which is orthogonal to your momentum p of this massive particle. And then whatever be the symmetry group which is so d minus 1 of this the space orthogonal to the p, and it will put in our particles that they irreducible representation of that d minus 1. And for photon, we have the two gauge condition. So let's say I represent the polarization of the photon, which is orthogonal to this plane, is defined by K1 and K2 vector. K1 is the momentum of photon 1, K2 is the momentum of photon 2, and this is the component with the orthogonal to the two planes. And by using the first condition, you can get rid of all, let's say, photon 1. So using the first condition, you can get rid of the K1 of this K1, let's say K1, K1. K1 is, let's say, it's a redundant. So you can just get rid of this. And using the second condition, because of that, this V1 is basically 0. So the photon polarization, which is effectively described by the component of it orthogonal to the scattering, orthogonal to the vector, which is we orthogonal to the plane spanned by K1 and K2. So hence it explains why it's the so D minus. So I think answer your question.
Yeah, but I don't understand why you are bringing in two photons. I mean, you can explain this using a single photon.
Yeah, I mean it's basically photon. Yeah, so it's basically two conditions, and hence you can just get rid of those degrees of freedom, and you are basically exploring.
But if you take a single photon, you can remove 2 degrees.
Yeah, I can remove the 2 degrees of freedom. So in that case, okay, you go to the
So we does it use 2 photons and close?
Sorry?
I'm not sure. Is it 2 photons?
So you mentioned about scattering.
Oh, okay. So you did it.
Anyone else waiting for updated momentum?
Sorry, I was just looking at the equations.
yeah, okay. So what you can do is you can go to the little group constructor. So you know that I mean I have this I told that I mean I will just construct this the little group, which is basically a subgroup of your not so let's consider the transformation, let's say L taken on the E such that okay, and let's say apart from I mean in this round group I found a subgroup of Lagrangian W which will map some vectors K to K. This is called the origin. And a photon I can describe by let's say A or minus. I can go to this place, I can describe this the construction of the photon. And that is so that I mean it's basically the plane which is in three I mean 3 plus 1 dimension. And then the set of vectors, set of transformation is leave this thing invariant if your that's explain why in 4 dimensions the photon has this the relative behavior. And you just do it in 5 dimensions. So I mean it's basically you do whatever the rotation you have in these 2 planes, it basically leaves your this vector invariant. So whatever the transformation leave your this vector invariant. So in high dimension you can just construct and it will be basically case of T minus. Yes.
Yes, Anusha's question was about why there are 2 groups. Why we're talking about 2. This is true for
It's for any, but it's as I am talking about the 3-point function of 2 photon and 1 matrix, it's very easy to show it. I mean that's how we parameterize our variable in this theory. So instead of basically talking about the full polarization, I will talk about the polarization which is orthogonal to the K1 K2 plane. And for massive particles, I will just talk about the polarization which is orthogonal to P, which is K1 plus.
Okay. You do need a traceless condition for the mass.
So these are places, like yeah, these are all places. These are all I mean these all 5 traceless vectors, traceless tensor with appropriate symmetry condition, and they are also going to P. So the independent things that we have is basically the polarization of the massive particle epsilon, which is orthogonal to P, the traceless polarization. And the polarization orthogonal to the K2 plane, and the momentum K1 and K2. But you can see that I mean as this thing is orthogonal to P. Okay, just remember the concept. So in this case, we will denote the group SO2, which is basically the rotation group, which is of the phase, which is orthogonal to K1 and K2, and the rotation group, which is SO3 minus 1, which is the rotation group of the plane orthogonal to this vector. Now I have to construct this polarization we have orthogonal to K1 and K2. These are we just contract these with any of the momentum. I mean either K1, K2 or P, these will give me 0. So then if I want to construct my momentum, I have to construct with this polarization, the polarization of magnetic particle. And this is orthogonal to this K1 plus K2. The only thing I can construct is basically K1 minus. So with these two vectors K1 and K2, I can go to a different, I can construct two different vectors, which is K1 plus K2, K1 minus K2. The only thing that will give me non-zero is K1 minus K2. So the only independent thing that I have is the polarization of these two photons, or more precisely the polarization orthogonal to this K1 and K2 of the photon, the polarization of these magnetic particles, and and if I can construct a scalar out of this quantity, and in this case I have two photons, so they could satisfy the both symmetry. That means if I interchange the photon 1 and photon 2, it should remain invariant. If I can able to construct such a structure, so they are valid in the of this superconductor. So the whole thing is boiled down to constructing a scalar of this quantity, which will satisfy, which will be invariant under one amplitude.
Why must it be a scalar? Why must the 3 point be a scalar instead of this? I mean, why have two polarizations?
Yeah.
So why must it be a scalar?
Why that must
Scalar means invariant.
Okay, so it's a scalar because the 3-point function, which has to be pointwise invariant. The 3-point variant. No, it's the interaction terms would be invariant. It's if you go to the Lagrangian. The scattering amplitude transform covariantly, but whatever the interaction you have,
Assume no interaction.
yes,
Not the scattering amplitude.
the scattering amplitude will be the covariant. Thing that I will include in the interaction.
Okay.
So before constructing the actual super function, let's do one more thing, which is basically I can take like I have described in this example of team, which is I can basically team is constructed of two vectors, but then I can further boil it down to a symmetric tensor, one antisymmetric tensor here. Then I can break the photon or the tensor product to tensor product of two photons into a symmetric traceless tensor. This notation is tensor. A antisymmetric rank tensor, and this is a scalar. And this is how they look like in terms of the polarization of the photon. And they are basically irreducible. Each of them are irreducible representation.
And your notation tells us what they are.
I'm sorry.
And your notation tells us what they are.
Notation tells us.
It's stress energy tensor.
Yes, I mean, And but in the notation of this, that's the so then let's see, I mean, how we can construct the different function. So let's consider a single case, which is the
So maybe I can specifically the previous slide. Yeah, for that symmetric part, is there a graviton hydrogen there? And how is it different from? I mean, you are combining two spin one massless particles, right?
Yeah.
So how is that expression different from that of spin two massless particles?
they are basically represented by the 10. I mean, if you look at the 10, they are same thing, but in terms of equation of motion and other things, they are basically I combined two photons and I created a different reproducible representation. That's different from the gravity.
So how would the representation, how would it look different?
For a
You know, a slide, yeah.
Okay, so they are basically same in terms of representation, they are same, but the graviton they have the satisfy different equation of motion. I mean, it's not the representation itself. They have to satisfy the equation of motion and other things. For graviton,
Two photons that together have spin two doesn't mean that you play gravity.
No, I'm not saying that. I'm saying how it is different.
In transform is the same as kind of stuff like this, so it's not a very complex. Two photons.
Right. But that I know. That's why it's a silly question.
but yeah, the equation of motion that they are. So let's consider a mapping particle and in the symmetric. So let's say it's the polarization of the particle, which is the symmetric resonance. And the photon, and let's say we want to construct whether the sequence function of this particle is the particle that is represented by this representation and a photon and two photons. So I can just form the algorithm is that I have to construct this symmetric meaning with any of the indices and they are symmetric, so I can construct them any of the indices. And the best thing basically I will construct is K1. And this is a valid sequence function for J event. J event is necessary for the boson. So this is a symmetric SUV, which is if we just interchange 1 and 2, it will be just even but there are J minus 2 such K1, and if I just interchange 1 and 2, this K1 to come to K minus. So for both invariants, or this thing to remain invariant under one fixing, I need this J has to be even. So this is a like sequence. So now this is in a moment of space, and I can basically my goal is to construct what are the terms that I have to include in the Lagrangian to represent such type of vector. So for that, so this is the algorithm to construct the sequence function, which is basically to construct the tensor which I got from the tensor property composition of the correlation of the antiparticles. And whatever the rest, I have to construct them with the vector K1 subject to the boson. And so when position means if I want to construct the what I just want to find what is the corresponding structure in the Lagrangian that will expect this kind of process, which is difficult. So this complex quantity H meaning that I have to construct from the field. H is the field length for photon, and this phi is the field for the massive particle. And I have to construct the Lagrangian in a K. And this is the transpose to the Lagrangian that will describe this type of interaction. Here. and J has to be greater than 2, greater than equals to 2, and they have to be even for. So now, I mean, this is the procedure, and then we can just classify this what type of interaction from being possible in different dimension. Why dimension? Because depending on dimension, this young tableau, they can have different number of rules. I mean, these are the number of rules possible in a young diagram, or that depends, that is the dimension you can say. So with this, I mean, and this type of interaction is not infinite. So for dimension D, which is greater than equal to 8, we have 3 and this total 6 type of circle. And no such circle is possible for dimension D with greater than equal to 8.
Nothing possible with D larger than 8.
No, this is the, I mean, at dimension D, this diagram is accurate. I mean, if you go 9, 10, 11, 12, or whatever, this type of circle will happen. Because, so as I told you,
Okay, D larger than 8. There are 6 kinds of interactions for D larger to 8.
these are available.
Thanks.
And this is basically in terms of the diagram and different the interaction in terms of which and quick. So similarly, you can just do the same process for two like a 4 dimension, which we are familiar with, and in 4 dimension the symmetric group of magnetic particles is 3 and for particles is 2. So this is the tensor particle composition. So here, I mean, the red thing, they represent the clarity or. So because they are taking with an extra, it's a 4 dimension field. And with this, you can see that I mean, there are only four possible such type of interaction possible. 2 of them are clarity given, 2 of them are clarity. And no other interaction is possible in 4 dimensions. So far, any questions?
I think you should call them 3-point functions. Point. You know, endpoint function normally endpoint correlate. It's typically how we use. It's just a suggestion.
Okay.
Published, I don't know.
No, yeah, we have included the other type of parameters, but we are not included. Okay, these are the 3.1. What are the possible sequences? And these are apart from the interaction, these are important because this type of this will tell you whether if you want to include the group and other whether these potentials are possible or not. So, for example, so if I just look at this, all the 4 dimensions, so either J is even in this upper case and the J is odd, but in the lower basically they have to be other. It also tells us that I mean, so in 4 dimension cannot or in a spin 1 particle can't decay into the photon. This type of from the standard model also know that this type of interaction is not there. In a spin 1 particle cannot decay photon, and for that it has to be mean 0, which is in this case or this case, and then those are basically the big field. So you include the interaction term, you include the higher connection, the loop connection, but it will tell you that those interactions are not possible. So now that we have yeah. So now that we have understood the interaction of photon with massive high-speed particles, we can also extend this to interpret the fermion. So fermion, or in this case, we will consider only the inner fermion of that type of possible. The fermion are complex. The Dirac fermion is complex representation of the Lorentz loop or the double curve of the loop. And to understand the Dirac fermion, we have to understand the default and in the default element. So in any event dimension, there are two types of Dirac linear is possible. One is either a non-finite, the either has a gamma star, and this gamma star is only possible in even dimension. And we can just and this gamma will be the metric tensor. And this linear transform as a tensor of that car. They understand Lorentz transformation. So let's represent the non-parallel term this way, the tensor of that car, this way. And they can only couple to a particles of this form, volumetric particles of this form. So there are there can be a column and no other forms here. And these are the interaction, the four types of interaction terms. Event action and have. These are their structure. The interaction term, the field space representation, and the Euro box is again after the momentum. And for odd dimension, we are only this two type of interaction. That's all. Again, you can get this thing for the same method. Yes. Okay.
Genuine question. Having done all of this work, what do you plan to do with these vertices and why all this trouble?
Yeah, so the goal is to get I want to start the superhuman intent with the genetic input. With the genetic input, not the speech. So I will so in the presence of let's say this is the interaction task that I have. Let's see if I want to study the symmetry high dimension because and the thing is that if I know some high dimension I can get dimension get the and this stuff appears for a genetic input. Genetic what value or a genetic input. Let's say instead of spin j I take spin j. What a I mean on top of that you just apply your on top of that you just apply your constant state of field. So let's say you got let's say spin let's say n equals to 1 take with 0 and then apply your operator get the state. So that is the because on top of that you just apply your supersymmetry generators and you take your depending on and so basically we want to we try to study these supersymmetry in dimension platform. And we see that we need to know this type of interaction, otherwise we can't.
Okay. Now the next question, extension to the J highly relatives, doesn't that mean that they're all irrelevant renormalization points?
So that will come at the loop level. If I just want to start the loop.
Sure, but what's the justification for in any circumstance studying Lagrangian with irrelevant terms?
No, it's not really well because let's say as I have told you the beginning. So yeah. For example, in this paper, they argued that if I want to include any high derivative correction by Einstein gravity, then I have to include all these type of things. Otherwise, Einstein gravity and we have to use that. If I include one high derivative correction, then we have to include this magnified field, the interaction of magnified field. There's no escape to satisfy the further.
So they're not irrelevant.
Yeah, they are not. But how they will satisfy the further?
I think in the beginning you mentioned, I don't know now if it's scattering amplitude or vertex. 7. But we're looking at the variance and the field rhythm.
No, what I'm saying is basically under field definition.
That leaves the rest of the Lagrangian.
But what the term even constant, which I can relate by field definition, those are basically same term. If I have two terms and they are related to each other by some field definition, they basically describe the same term.
Only if that the definition means the rest of the Lagrangian value.
Yeah.
So that's what it means. So strong points. Okay.
If we include all these high derivative terms with the equations of motion, we'll get higher order equations of motion.
Yeah.
To try to solve those, we need more data. So it's no longer just initial position, initial momentum, but initial acceleration and the stuck in there. Does it make sense to write down stuff in this way when your initial condition data now becomes this rather strange? Does it satisfy a Gaussian? Can you satisfy a Gaussian condition? Can just be position first derivative information? Now over here you're going to have equations of motion.
But we usually most of the things we study whatever. You have your you define the field, and then you used to study them further.
The problem that you're describing we already have in QED, right?
Now that's getting much worse.
Second question.
Yeah.
That's good. Retarded or advanced propagation.
Yeah.
We don't know how to study them properly. For the simplest interaction, we study them further. The most.
One question added to Warren's question. Is there a problem with the causality of higher derivatives?
Yeah. If you include one hydrogen collection to one gravity, they will most likely will create problems for that. To get rid of it, you have to include infinite power of this interaction. So that's the.
So theories with higher swing, do they suffer this problem?
Theory with high spin, if you just include finite number of them, they will perform this problem.
What is your include an infinite number of times? If you include infinity in the swing, then all problems go.
But then you have a different source out of
Basically, limiting that, I mean, it's strict.
Yeah. So it's a Hilbert Potter form.
Okay, let's leave it at that. Thanks a lot.